Problem number 9. A potential difference of 6 nanovolt is set up across a 1.5 centimeter length of a copper wire that has the radius of 2 millimeter. How much charge drifts through a cross section in 4.7 millisecond? First of all, let's rewrite the given first. So in this question, they gave the information about the potential which set across the copper wire, and the material of the wire is a copper. So we are going to write the given first. V, which is equal to 6 nanovolt, so which is 6 multiply 10 to the power of minus 9 volt, and the length of the copper wire is 1.5 centimeter. So in terms of meter, which is 1.5 multiply 10 to the power of minus 2 meter. And here the radius of the copper wire is given, because if you see the cross section view of the copper wire, it looks like area of the circle. So area of the circle is pi r square. So here the radius of the copper wire is given is 2 millimeter. So in terms of meter, which is 2 multiply 10 to the power of minus 3 meter. Now what we are going to find? We are going to find the value of the charge. So when you give the potential across the copper wire, what will happen? The charge will be drift through the cross section. So in time 4.7 millisecond, how much charge will be drift across the cross section? So that means we are going to find the value of the charge. So at time t is equal to 4.7 millisecond, we are going to find the value of the charge. So milli stands for 10 to the power of minus 3. So which is 4.7 multiply 10 to the power of minus 3 second. So better we can draw the diagram for this question. You have a wire, and this wire is a copper wire, and its length is 1.5 centimeter. So length which is equal to 1.5 centimeter. And if you see the cross-sectional view of the copper wire, it looks like area of the circle. So it has the radius r, which is equal to 2 millimeter. And you set a potential across this copper wire. So the value of the potential you set is 6 nanovolt. And now we are going to find how much charge will be drift at time t is equal to 4.7 millisecond. Clear, brother? Okay. Now, what formula we are going to get the value of the charge? Because in this chapter, we studied a lot of formulas. So here, for this question, we are going to use the equation Q, charge, which is equal to the current multiplied by time. So this is our main equation. We are going to get the answer for the charge. Now we have to see the given first. So what are the informations we have here? For example, here our equation is Q, which is equal to I multiplied by T, but time is already we have here, which is already given in the question, but there is no information about the current. So now what I'm going to do, I'm going to use the formula for the current. What is the formula for the current? As we already studied, potential V, which is equal to current multiplied by a resistance. And from this formula, we can easily get the answer for the current. Therefore, the current, which is equal to potential V over the resistance R. So now what I'm going to do, I'm going to take this current formula, I'm going to substitute that value, substitute that equation here. When you substitute the equation for the current in this main equation, our equation will be modified as Q, which is equal to V multiplied by T divided by R, right? Now we have to see again. And here, once you substitute the value, once you substitute the equation for the current here, now we have the information about the time as well as the potential. But there is no information about the resistance. You can see the given value here. There is no information about the resistance. So for this, we are going to use the resistance equation, R, which is equal to the resistivity rho multiplied by length divided by the cross-sectional area. Now what I'm going to do, I'm going to take this resistance equation, I'm going to substitute here. If you substitute, again, our main equation will be modified as Q, which is equal to potential multiplied by time divided by, when you substitute this equation, rho L over area will be coming like this, but this area will go to the top of the equation. Am I right? So top of the third equation. So by that, your equation will be potential V time area divided by the resistivity multiplied by length. So this is our modified equation, right? Now, again, we are going to see the information. Here we have the information, we have the values for the potential voltage, we have the value for the time, and also we have the length and the resistivity for the copper. What is the value of the resistivity of the copper? Better we can just see the chart here. So here we have the copper, and the resistivity of the copper value is 1.6 multiply 10 to the power of minus 8 ohm meter. So we have the constant value for the resistivity also. So the resistivity value for the copper is 1.69 1.69 multiply 10 to the power of minus 8 ohm meter. So now you can see here we have all the details, but we have to substitute the answer for the area. So as I already mentioned, if you see the cross-sectional view of this copper wire, let's we go back to the diagram. If you see the cross-sectional view of this copper wire, it looks like area of the circle. So as we already know the formula for the area of the circle A, which is equal to pi r square. So now I'm going to take this rule, I'm going to substitute here. By that, our equation will be modified again as Q, which is equal to potential V multiplied by time, and in this place of area I'm going to use pi r square divided by the resistivity of the copper value multiplied by length. Now you can see we have all the values right now. We have the answer for, we have the values for the potential difference which set across the copper wire, and we have the time value, and we have the radius of the copper wire, and also this wire is a copper wire. So we have the constant value, the resistivity of the copper value we already have, which is 1.69 multiplied 10 to the power of minus 8, and also the length of the copper wire we have in this question as 1.5 centimeter. Now I'm going to substitute all the values to get the answer for the charge. So now what I'm going to do, I'm going to substitute the value. Q, which is equal to, the potential is 6 nanovolt. You can just go back to the question as I already write all the given here. So better you can just see all the values. Now I'm going to substitute all the values in this equation. We have the potential of 6 nanovolt. We have the length of 1.5 centimeter. Radius of the copper wire is 2 millimeter. And the time, in this time, how much charge drifts, we are going to find. So time value is 4.7 millisecond, and also this wire is a copper wire. So the resistivity of the copper value is a constant, which is 1.69 multiplied 10 to the power of minus 8. I'm going to substitute all this value in this last equation. So this is our final equation. Now I'm going to substitute the values to get our final answer. So what is the value of the potential? 6 nanovolt. So 6 multiply 10 to the power of minus 9, and the time is 4.7 millisecond. So 4.7 multiply 10 to the power of minus 3 second, and the value of the pi we know, which is 3.14, and the radius of the copper wire they mention as 2 millimeter. So in terms of meter, 2 multiply 10 to the power of minus 3, this is square, so we have to square this value divided by, and the resistivity of the copper wire is a constant, which is 1.69 multiply 10 to the power of minus 8, and the length of the copper wire is 1.5 centimeter. So we have to convert that 1.5 centimeter to meter. So 1.5 multiply 10 to the power of minus 2. So now I'm going to multiply the top as well as the bottom, and after that I'm going to divide the top with the bottom value. So let's see what is our final answer. So I'm going to calculate this value. So just wait. I'm going to use my calculator. 6 multiply 10 to the power of 9 multiply with 4.7 10 to the power of minus 3 multiply with a pi value multiply with 2 multiply 10 to the power of minus 3 the whole square divide by 1.69 10 to the power of minus 8 multiply with 1.5 10 to the power of minus 2 here I got the answer as 1.397 multiplied 10 to the power of minus 6 coulombs. So what's the final answer here? I got here as 1.397 multiplied 10 to the power of minus 6, and the unit for the charge is coulomb. So the final answer for this question, because we are going to find the answer for the charge, which is 1.397 multiplied 10 to the power of minus 6, and the unit for the charge is coulomb. So this is our final answer. That's it. Thank you.